This is the third and final impulse momentum problem I'm going to do, and I've picked it for a number of reasons. First of all, this is a classic problem where you're given a very short impact time, in this case 0.75 milliseconds or 0.00075 seconds, and they ask you to find the average force during that time. And so you have a velocity coming in, this impulse, and a velocity going out, and the force over that time is the impulse, and you do some vector subtraction and you can get what the force times delta t should be, the impulse, and once you get that, you divide by delta t to get the force. That'll be clear. The next thing I picked it for was that this is a good review for projectile motion. So let's start with that. And so what you have is you have V2 at 30 degrees. Okay, so it's 15 degrees to V1 and another 15 degrees to V2. And then it'll travel 100 meters. And it'll be at a height of 2.5 minus 0.75, which is the height of the mitt minus the height of the impact. So 2.5 enter 0.75 minus 1.8 meters. So this height there is 1.8 meters. Okay, so what we know is that the y acceleration is minus g. The x acceleration is 0. The x velocity initially is v2 cosine 30 degrees. And the y velocity initially is v2 sine 30 degrees. Okay, so the equations of motion, we know that x will be v2 cosine 30, that's the velocity, initial velocity, which doesn't change because acceleration is 0, times t. There's no acceleration, will equal 100 meters. The y, which will hit, which is given by vy, which is v2 sine 30 degrees times t, and there's an acceleration, so when you integrate that, it ends up being minus 1/2 g t squared, and that will equal 1.8 meters. So let me write everything out. So root 3 over 2 v2 times t will equal 100. 1/2 v2 times t minus 1/2 of 9.81, 4.905 equals 1.8. And we're trying to solve for V2. So I'm going to solve equation 1 for t and then plug it into equation 2 and solve for V2. I'll take a break and do it and come back. Okay, so I solved equation 1 for t and then plugged that into equation 2 and then solved for V2. And this is what happened. Okay, we get V2 is 34.2 meters per second. So that's the projectile motion part. So now we can start the impulse momentum problem. So here's the impulse momentum problem. This ball is coming in at 15 degrees at 30 meters per second, and the batter hits it, and it leaves at 30 degrees at 34.2 meters per second. So this is before and this is after. So let's write out the equation. So it's mv1 plus integral f dt equals mv2. And for now, I'm just going to call integral f dt just the impulse. So if you write that out, you get at 15 degrees, 30 meters per second, plus this vector I will equal going out, let's see, at 30 degrees, 34.2 meters per second. And so we need to solve for I, the impulse. And so this is now complicated enough where I don't think I'm going to draw triangles and do law of sines and law of cosines. What I'm going to do instead is I'm going to break this down into its vector form. Oh, and this is times the mass and times the mass. So the first one will be the mass times minus 30 cosine 15 degrees in the x direction and minus 30 sine 15 degrees in the j direction, plus the impulse vector will equal the mass times 34.2 cosine 30 degrees in the x direction plus 34.2 sine 30 degrees in the j direction or y direction. So you solve for I. So you bring this to the other side, so you have m times 30 cos 15 degrees I plus 30 sine 15 degrees j plus m 34.2 cos 30 degrees I plus 34.2 sine 30 degrees j. And let me punch that out and get back to you. So plugging in all the sines and cosines and multiplying it out gives this. Okay, and then I'm going to collect all the I and j terms and come back. And collecting all the I and j terms gives this. And so finally, to get the impulse, I'm going to put in the mass, which was the ball. I got to go look that up, figure out what the mass of the ball was, and then multiply it through. I'll be right back. So I read the problem statement, and the mass of the baseball is 0.15 kilograms, and so there you go. Multiplying 0.15 times those numbers gives the final impulse of 8.79 I plus 3.73 J, and the units of impulse are newtons times second. But what they want is the force. So we know that the force times delta t will be the impulse. And so the force is just going to be the impulse divided by delta t. And delta t was very small. It was 0.00075 seconds. So it's that'll be 8.79 I plus 3.73 J divided by 0.00075, and that equals 11,700 newtons in the I direction and 4,000 or 5,000 newtons in the J opposite direction. It's actually 4,972, so I rounded it to 5,000. And I'm writing in kilonewtons. And so that's the average force. So the bat puts a force of 11.7 I plus 5.0 J kilonewtons on the ball. The solution in the solution manual is completely wrong. It's for the wrong problem or something, so there's no way to check this.